This is going to be the lecture over chapter 29, section 2. We're going to take another look here at atomic structure. So we can imagine constructing a neutral atom by starting out with a bare nucleus with Z protons and adding Z electrons one by one, respecting the Pauli exclusion principle. So to obtain the ground state, we fill the lowest energy states, in other words, those closest to the nucleus, with the smallest values of N and L first. And then we fill successively higher states until all of the electrons are in place. By filling the atomic states, we begin to learn the chemical properties of atoms, which are determined principally by interactions involving the outermost electrons. So we have our nucleus here, we have our 1s subshell, which is here, and you can see 2 electrons are in that, and then you've got the 2s subshell here with 1 electron in it. So we're going to use that exclusion principle along with electron energy states to derive the most important features of the structure and chemical behavior of multi-electron atoms, including the periodic table of the elements. Number of electrons in an atom in its normally electrically neutral state is going to be called the atomic number, and that is going to be referred to as Z. The nucleus contains Z protons and some neutrons. Neutrons have no charge. The proton and the electrons have the same magnitude of charge, just opposite signs. So in the normal atom, the total electrical energy or charge is 0. Because the electrons are attracted to the nucleus, the quantum states correspond to regions nearest the nucleus have the lowest energies. So we can imagine constructing an atom by starting with a bare nucleus with Z protons and adding Z electrons. To obtain the ground state, we fill the lowest energy levels first, and then we fill successively higher energy states until all the electrons are in place. And as we fill up these states, we must be careful to pay careful attention to the limitations imposed by the exclusion principle. The chemical properties of an atom are determined principally by interactions involving the outermost electrons. So we want to particularly learn how those electrons are arranged. So again, if we look at the ground state electron configurations for the first few atoms, order of increasing Z. For hydrogen, the ground state is 1s. The single electron in the state is given by this set of quantum numbers. In the helium atom, both electrons are in the 1s state with opposite spin components. And we denote this configuration as 1s squared. Because the 2 electrons in the helium atom have different spin quantum numbers, they are in different quantum mechanical states. This, of course, is required by the Pauli exclusion principle. So for helium, the K shell is completely filled and all others states are empty. Helium is an inert gas and it has no tendency to gain or lose an electron, and ordinarily it forms no compounds. Matter of fact, helium was something that we only discovered really whenever we started looking at spectral lines and determined there should be an element there. And since it's technically lighter than air, you don't really see it around anywhere. So that was kind of an interesting little history there on helium. Lithium has 3 electrons in the ground state. 2 are in the 1s, and then 1 is in the 2s state. And you can see the configuration here. The exclusion principle forbids all 3 electrons from being in the 1s states. On the average, the 2s electron is considered farther from the nucleus than the 1s electron. Thus, the net charge influencing the 2s electron is approximately positive E rather than positive 3E, as it would be without the 2 1s electrons present. The 2s electron is loosely bound, only 5.4 eV is required to remove it. compare with 13.6 eV needed to ionize the hydrogen atom. In chemical behavior, lithium is an alkali metal. It forms ionic compounds in which it loses the 2s electron. In chemistry, these electrons that participate in the formation of chemical bonds are commonly determined as valence electrons. Lithium has one such electron, so its valence is +1. The valence is positive because the 2s electron is lost in the bonding process. Next comes beryllium. You can see its ground state configuration with a filled K shell and 2 electrons in the L shell. And then so on and so forth. And you can see here in this particular chart how the electron configuration starts to build up. You can see by the time you get down to zinc, you got quite a bit going on. So X-ray energy levels, the outer electrons of an atom are responsible for optical spectra. Their excited states are usually only a few electron EVs above the energy of the ground state. In transitions from excited states to the ground states, they usually emit photons in or near the visible region, with photon energies about 2 to 3 eV. There are also X-ray energy levels corresponding to vacancies in the inner shell of a complex atom. In an X-ray tube, an electron may strike the target with enough energy to knock an electron out of an inner shell. These inner electrons are much closer to the nucleus than the electrons in the outer shell. They are therefore much more tightly bound, and hundreds of thousands of EVs may be required to remove them. So let's say, suppose an electron is knocked out of the K shell. The atom is then left with a vacancy, and we'll call this state a K X-ray energy level. This vacancy can be subsequently filled by an electron falling in from one of the outer shells. The transition is accompanied by a decrease in the energy of the atom because less energy would be needed to remove an electron from the LMN shell. And an X-ray photon is emitted with energy equal to this increase. Each state for any specific element has a definite energy, so the emitted X-rays have definite wavelengths, and the spectrum is a line spectrum. If the outermost electrons are in the N shell, the X-ray spectrum has 3 spectral lines resulting from transitions in which the vacancy in the K shell is filled by the L, M, or N electron. This series of lines is called the K series, and you can see that it shows the K series for tungsten, molybdenum, and then copper. There are other series of X-ray lines called the L, M, and N series, produced by an ejection of electron from those shells rather than from the K shell. Electrons in these outer shells are farther away from the nucleus and not as tightly held, so that it requires less energy to remove them, and the X-ray photons emitted when these vacancies are filled have lower energy than those in the K series. And you got a few problems there to work through.